All right, would you guys agree that mathematically speaking, you have encountered situations in a math class, processes in a math class where you use it for a couple of days, but then you feel like you've never used it again? And that happens, okay? Now, that math is important somewhere, but maybe we don't use it very often. We've used complex numbers, okay? You guys have dealt with like A plus BI stuff, but you don't maybe have right now a real application for that, okay? If you were going to be maybe an electrical engineer, now you have a huge application for A plus BI, okay? Awesome, okay. Not yet, okay? So, when we are going to go through and learn in the next several days of how to develop a comprehensive graph and the strategies and tools, techniques I teach you in order to do that, I want to make sure that we understand that how important our factoring is, okay, and how important the techniques of factoring that I provide you are going to be, because of what happens when you get into a calculus class, okay? Today, we're going to start with maybe something like, I don't know, 2x to the third plus 4x squared plus 8x plus, I don't know, let's just stop there, just 8x, okay? And we're going to learn, obviously, hopefully we already know what the end behavior of this looks like. We'll factor this, so if I factor it, all right, it gives me that kind of stuff, so I get 1, 0 at 0, 0. This stuff here, because it's not factoring, is going to tell me basically the other two zeros are complex numbers, okay, they're non-real solutions, which is great. But I don't know whether I've got any maximums or minimums or any thing like that. So what we'll do, don't want this in here anymore, is in calculus, we'll take and say, okay, take that previous 2x cubed plus 4x squared plus 8x, and we'll find what we call the derivative. Okay? The derivative is ultimately a equation, or a function, I guess, that's telling me the slope of my curve at every x value that I want, okay, or any x value that I want. So what's nice is that maximum minimums, the slopes of those tangent lines that we're looking at then when we find a derivative, the slopes of those are 0 at maximum minimum. So if I solve the equation for 0, so if I that equals 0 for x, and I get that, okay, so it basically tells me now that I don't have any maximums and minimums, and then solve it, right? Does that make sense, everybody? It's solution, okay? If I do opposite of B or a C for that thing, I think the discriminant is going to have to be negative. In order to do that, in order to maximum minimum, you have to know. Okay, so I guess to show you the derivative and what's happening with this, look at this expression here. Okay, take the 2x, take that 3 and multiply it by the 2. They give you 6. Subtract 1 from that, it gives you the power of 2. Okay, take the 4 times the 2, they give you 8. That's my b term now. Take and subtract 1 from that 2, gives me a 1. The 1 here times the 8, it gives me 8. That exponent gives you x to the 0. So that is now our that's our derivative. Okay? You don't need to know any of this stuff. You don't need to write any of this stuff down, guys. But I want you to see the importance of it. So what happens then next is, okay, we start with, maybe something to the 5th power. Maybe we then have a 3rd power and maybe something squared. So I look at that. And I then ask, okay, what is the derivative of that? And I get that. Okay? So today, guys, and Monday, Tuesday, Wednesday, we will work on factoring that 2x to the 5th, which is something we haven't dealt with yet this year. Okay? You dealt a little bit with factoring those types of things last year with P over Q. Remember hearing that phrase? Synthetic division, long division. All right? So you've done a little bit of the process. We'll get better at this. You'll reteach it this year. But we'll factor that to find the zeros. Okay? But if I want to find the maximums and minimums, their precise location, I have to factor that. Is that all right with everybody? Okay. In factoring that thing, we'll probably incorporate the same factoring techniques after the top one. All right. So our factoring becomes a huge tool for us to not only eventually to find maximum minimums as well, points that are not on the x-axis. Okay. Now, why don't we do that now? Because we haven't talked about limits. We haven't talked about how we can create a derivative, what a derivative really is, and all that kind of stuff. There's about 2 months worth of preliminary information in calculus to discuss before we actually start doing that. Okay. But what that's called is when you get to calculus, you'll hear what we call a first derivative test. Okay. And you'll also hear what we call a second derivative test. And basically, they are techniques that help us determine what is happening at maximums and minimums, where they're occurring for our functions. Is that all right? Right now, since we don't have that ability, we're going to have to do test points. Okay? We're going to have to create a T-chart and evaluate, which is not all that convenient, it's not all that enjoyable, and it's really not all that accurate in regards to seeing what my graph is doing around my extremes. Okay? Really, the only graphs that you have the ability to, or polynomials you have the ability to kind of hone in on exactly what the extremum is a quadratic. Okay? Maybe as we move on, we'll deal with cubics, and I'll show you how with the derivative to find the maximum minimums exactly as it deals with cubics. But that might take away from some other stuff that we have to get through. We kind of talked about this the other day. We didn't get into a whole lot of details, but it's kind of the last theorem that we're going to deal with in regards to the information we need to develop a comprehensive graph. Okay. Obviously, again, when I say comprehensive, that's kind of a vague word. Okay, because until next year, you won't have the tools to make it comprehensive. But that's what we're trying to strive towards. But it says if you start with polynomial p of x, okay, and its leading degree is n, okay, then the graph has at most n minus 1 local extrema, meaning the local maximums and local minimums, the total, can only, the most it could have is 1 less than the degree of the polynomial that you start with. So I have a 5th degree polynomial. I could have at most 4 turning points. Okay. Now, at most means that's maximum. It means I could have less. Okay. But we'll start to look at and analyze, okay, can I have 3? Because if I have 3, does it match up the end behavior, okay, that a 5th degree polynomial should have had? And we'll talk about that. It doesn't. Okay. So we'll talk about, as we start to see examples here, the potential number of extrema you can have for a curve. All right. Right now, at most, it's n minus 1. But then we can start to say, okay, it could potentially, if it's a 5th degree, it could have 4. But there's no way it could have 3. But it could have 2. No way it could have 1. But it could have 0. Think that makes sense? Okay. And we'll talk about that as we start to investigate some specific examples. All right. So what we're doing, guys, when we get one of these graphs is we know the end behavior, so we know what it's going to do in the long run. We should have the ability to find the zeros and the y-intercepts pretty easily. We then know, based off our multiplicity, the behavior of the graph around those zeros. We have the ability, when we have our zeros and we have our theorem in front of us here, the n minus 1 for local extrema, we have an understanding then of what our graph should look like, kind of around the x-intercepts, okay, or in regards to x-intercepts. We don't necessarily know how tall the graph is going to get or how low the graph is going to get for our max and mins, though, and that's the thing that we'll continue to work to get better at. All right, so I want to do some examples today. That's kind of really all I've got planned, is see maybe 2 or 3 of these, and then kind of reverse the rules and start with a graph and see if we come up with the equation from a graph. Okay. So P of x is equal to x plus 2, x plus 1 squared, 2x minus 3. Right now in this section, guys, they're not introducing any new factoring techniques. So you could give, they could give you a P of x like this, or they could give you a P of x expanded. Okay. If it's in expanded form or polynomial form, then they're providing you one that can be targeted with all of your factoring techniques that we talked about in the first kind of 3 or 4 weeks of school. Okay. So this one here, if I were to look at this, get my solver out here, say expand. So all it does, if I hit expand, all it's going to do is FOIL this out for me. Okay, so in this section, they will not give you a expression like that one there, the 2x to the 4th plus 5x cubed minus 2x squared minus 11x minus 6, because we don't have the tools yet to factor that. Does that make sense? But they might give you something like 6x squared plus 8x plus 2, that one underneath it, because you do have the ability to factor that. Does that make sense to everybody? So if they give it to you in polynomial form, they're telling you use one of your factoring techniques that you currently know. Next week we'll target then, okay, if that thing in polynomial form is exactly the same thing as what we have written up here in the PowerPoint, how do I go from that to that? And that's what we'll work on next week. You guys remember synthetic division, right? Just remember doing long division. Long division, synthetic division are analogous. Synthetic is just a quicker way of writing it down. And you use P over Q. It's called the rational root theorem. That's what we'll get into in order to find that polynomial kind of depreciated x plus 2, x plus 1 squared, and 2x minus 3. All right, so I want to sketch a quick graph of this, and let me see if this might be a better way of doing this if I can. Obviously, this is a lot better, guys, if we have graph paper. And even at that, it might not be great. And even with GeoGebra, because I can only see, you know, from -6 to 6 and -3 to 3 on these axes, it might not be all that conducive to do this on GeoGebra either. But let's say that we had what P of x was equal to x plus 2, x plus 1, that squared, and then 2x minus 3. We're going to have to pause this in a minute. I'm lagging.